Hi everyone, I'm Fanchen, a PhD student at KAIST. Today I will introduce our work titled Identifying Group Anchors in Real-World Group Interactions under Label Scarcity. First of all, what are group interactions? We, human beings, are social animals, often doing activities in groups. Group interactions are interactions that happen among a group of people, and they are everywhere in our lives. For example, multiple scholars can co-author a paper, multiple users can participate in online Q&A session, and so on. One interesting observation we have is that in real-world group interactions, in each group, we often find a particularly important member that brings other members together. For example, for a paper, the first or last author is often the person who initiates the project. For an online Q&A session, it's because of the user who asks the question that all the other users can participate and answers or discusses the question. We call such a person the anchor of the group, and in this work, we study the problem of identifying such anchors in real-world group interactions. So why is it an important problem? Identifying group anchors has several practical applications. The most immediate application is group interaction prediction. As we just mentioned, anchors often initiate group formation and bring together the other members. Therefore, identifying group anchors can help us predict future groups, such as academic or business collaborations. Also, since anchors play important roles, identifying and understanding them helps group management. For example, in social media communities, keep those anchors active can be essential to keep the whole communities active. When doing marketing, it can be much more effective to find the anchors and reach them compared to just reaching to random members. Mathematically, we formulate the problem of group anchor identification as an optimization problem on hypergraphs. Hypergraphs are generalizations of graphs consisting of nodes and hyperedges. In our case, each node represents a person, and each hyperedge represents a group interaction among multiple people. Here we have an example of co-authorship hypergraph, where each node is a scholar and each hyperedge represents a publication in which the nodes are the authors co-authoring this publication. To formulate this problem, we further introduce two concepts, domains and anchor rows. We consider real-world hypergraphs with specific domains. The domain can be co-authorship, online Q&A, email, and so on. Each domain has its own anchor row, that is, the row of group anchors in that domain. The anchor row of each domain considered in our work is listed below. Note that for co-authorship, either the first or last author is arguably the anchor, and we consider both alternative cases. Now we are ready to define the problem. So given a real-world hypergraph where each hyperedge is a group, and we know the anchor in some groups, we consider the realistic scenarios under label scarcity. That is, we only know the anchor in a few groups. The task is then to predict the anchor in each of the remaining groups. In the example below, we know the anchor in two groups on the left, and we want to predict the anchor in the group consisting of 3, 4, and 5, and the group consisting of 4, 5, and 6. An important property of group anchors is that they are group dependent. For example, the node 4 is the anchor in the group 1, 2, 4, but this does not mean it's also the anchor in other groups. Vice versa, 6 is not the anchor in the group 6, 7, 8, but it's still possible to be the anchor in other groups. Specifically, it is totally possible that here 6 is the anchor in the group 4, 5, 6. Our high-level idea to approach this problem is to use an observation-driven approach. That is, We first do observations on real-world group interaction data, then we identify the patterns in those data, and finally, we design a lightweight method based on those patterns. We consider such an approach mainly because of two considerations. First, as mentioned before, we focus on realistic scenarios on the label scarcity. In such cases, complex models, such as deep learning-based ones, may fail, while an observation-driven model is more robust. Also, the observation-driven nature makes our method more intuitive and interpretable instead of being like a black box. That said, let us first introduce our observations. For that, we first introduce the settings. First, since we consider our problem under label scarcity, we impose the same constraints for our observations to ensure that they are relevant. Second, we assume no external features are given other than the hypergraph topology itself, which is true for the datasets we use. Here are the datasets we use in our work. We use 13 datasets in total from 5 different domains. Okay, now we are ready to describe our observations. Recall that we only have information from two parts. First, the hypergraph topology itself, and second, label information of the non-group anchors. The first observation is about the first part, the topology. From topology, we can obtain various topological features, but are they helpful? Thankfully, yes, they are. Specifically, we observe that using only topological features, we can identify group anchors with a fairly high accuracy. In other words, topological features are quite indicative of group anchors. We also have some intuition behind such an observation. Let's take a simple feature, node degree, to explain this. In a co-authorship collaboration, a node with high degree is likely a senior scholar, and she is more likely to be the last author. In an online Q&A session, a node with low degree is likely a new user, and she is more likely to ask a question. Here we can also see the domain dependence, that is, the anchors in different domains may have different topological characteristics. Let us provide some numerical evidence too. Here, we show the accuracy of predicting the highest degree or lowest degree node in each group as the anchor, and compare such a simple method with SOTA deep learning baselines. As we can see, such a simple method achieves considerable performance. As discussed, we have two parts of information, and observation 1 focuses on the first part. Now, our second observation focuses on the second part, that is, label information of the non-group anchors. We mentioned that anchors are group dependent, but are the anchors in different groups completely irrelevant, or can we still find some correlations across different groups? Thankfully, yes, we can. Specifically, we observe that if a node is the anchor in some groups, then it's likely the anchor in other groups too, and vice versa. Similar to observation 1, we also have some intuition for this observation. Imagine, for example, for co-authorship group interactions, if a person is the last author of several papers, then she is usually a professor. Then she is likely the last author of other papers too. Then we show some numerical evidence. We first define the concept of anchor purity of each node V, which is the probability that V is the anchor in both or neither of two groups, when we randomly pick two groups containing this node V. We then compare the average anchor purity in real-world group interactions and the randomized ones, and show that the anchor purity in real-world group actions is significantly higher. We then further analyze the possible mechanism behind such an observation. We have the hypothesis that each node V has a global anchor strength that indicates the overall likelihood of the node V being the anchor and is shared across all groups involving V. We also numerically validate this hypothesis. For each node V, we define its anchor proportion as the proportion of groups where V is the anchor among all the groups involving the node V. We show that we can well explain the non-group anchors using the anchor proportion as the anchor strength we hypothesized. This implies that such global anchor strengths indeed exist. But note that this is not a method, since the anchor purities are computed based on non-group anchors and are used to explain those group anchors. So this is only used to validate that such global strengths that can well explain the anchorship in real-world correlations indeed exist. Based on our observations, we built our method called Anchor Radar. Here is an overview of it. It has two stages corresponding to our two observations. In stage 1, we train an MLP to learn topological scores to fit non-group anchors. In step 2, we train anchor strengths while using scores from stage 1 as references. Let's look at stage 1 first. As mentioned, stage 1 is based on observation 1. Recall that observation 1 says that topological features are informative about group anchors. Therefore, we aim to train a model to exploit such correlations between topological features and anchorship. As mentioned, we use a lightweight model, specifically an MLP. And in stage 1, we use topological features as the only inputs. The objective is to fit the non-anchors. Here are some details of stage 1. For the topological features, we followed existing works and used 4 different measures for each node. Based on those 4 measures, we build X using both hypergraph level, which is global, and group level, which is local, aggregations and normalization, which results in a feature vector for each node group pair VE. Each node group pair VE has its topological score, and a higher score means that the node V is more likely the anchor in the group E. Each score is computed from topological features X and transformed by an MLP. The loss function L1 is minimized when in each group its anchor has a higher score compared to the other non-anchor nodes. After stage 1, we now have topological scores for the node group pairs. Specifically, for each node V, its scores are defined locally within each group E. Now, let's look at stage 2, which is based on our observation 2. Recall that observation 2 talks about the cross-group stability of anchorship, and we have a validated hypothesis that each node V has a global anchor strength shared across all groups involving V. From stage 1 to stage 2, we will go from local scores to global anchor strengths. Specifically, we learn global anchor strengths with 2 objectives. First, just like the stage 1 scores, the strengths should match the known anchors. Second, the strengths should align with stage 1 scores. Here are some details of stage 2. For the first objective, the loss looks similar to what we had in stage 1, except for that the stage 1 scores are replaced by stage 2 anchor strengths. For the loss is minimized, in each group E, its anchor should have a higher strength compared to the other non-anchor nodes. For the second objective, we designed the loss function so that when it's minimized in each group, the relative relations of the nodes in it with regard to stage 1 scores and stage 2 strengths are aligned. For example, in the group, the node with the highest topological score ideally should also have the highest anchor strength. Then the final loss is a weighted sum of the 2 sublosses with a loss term coefficient alpha2 that adjusts the emphasis between them. After training, we get to learn global anchor strings, and for each group E, we get an A hat E, which is the node with the highest anchor strings. After getting those A hat E, we further do global aggregation. For each node V, we aggregate its either ground truth or predict anchorship from all the groups containing V. This gives us globally aggregated scores, and based on them, we get the final prediction A tilde E for each group E. So why do we do this global aggregation? We are inspired by majority vote. By aggregating predictions from different groups, we can correct local errors and get more robust predictions. In the example below, we can see that the global aggregation corrects the local error in a group. We have introduced the datasets once before when we discussed our observations. Let us recap that we use 13 datasets from 5 different domains. We consider the realistic scenarios on the label scarcity, specifically with a 7.5 to 2.5 to 90 trend validation test split. For baselines, since we are the first to define and consider this problem, we couldn't find immediate competitors. Therefore, we adapt existing methods proposed for a related problem. In total, we have 9 baselines. Let's look at the results now. First, the proposed method achieves the highest accuracy in identifying anchors in real-world group interactions. We believe that this superiority comes from our lightweight and observation-driven design of our method, which is more effective and more robust under label scarcity. With a lightweight design, the proposed method uses on average 10.2 times less training time compared to the fastest baseline. Also, it uses on average 43.6 times fewer learnable parameters compared to the most lightweight baseline. Then we have the ablation studies. We consider variants of the proposed method, each excluding one of its components. We show that the full-fledged version outperforms the variants, showing that each component is helpful, especially the synergy between the two stages. Moreover, we also show that the anchor strength learned by the proposed method is helpful for downstream tasks. Specifically, we consider group interaction prediction, or more precisely, distinguishing real and fake group interactions. We use villain, a self-supervised method, as the backbone, which also does not need external features as inputs. We show that the performance of villain is even better when we include additional features from anchor strengths. To summarize, we proposed new concept called group anchors and the problem of identifying them in real-world group interactions. We made observations on real-world group interactions about anchors and extract patterns. Based on those observations and patterns, we developed our method Anchor Radar. Through extensive experiments, we show the empirical superiority of the proposed method. For more details, you can read our paper and check out this link for our GitHub repo. Thank you for your attention.